Okay, we look at three other types of distributions today. The first one is defined right here as a multinomial. Yesterday we looked at a binomial. A binomial had two possible outcomes. A multinomial has more than two possible outcomes. Very simply stated, much like our binomial, our probabilities have to stay the same for each trial. So regardless of whether I select the first or the 50th item, the probability of getting that item is still the same, and the outcomes are independent from one trial to the next. Identifying our variables here, just looking at our formula here for a multinomial, n factorial over x1 factorial, x2 factorial, blah, 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 up to xk factorial. Then that fraction is being multiplied by the probability raised to the x power of each of our individual categories. So identifying our variables, n is our total number of trials. X is the number of times we want each individual event to occur. So within our total number of trials, we're going to break that down into different categories. So X is the number we want in each category, and then P is the probability for each of those individual categories. Probably easiest to illustrate here in this example, the probability of an A in a certain class is 0.1, a B is 0.2, a C is 0.5, and lower than a C is 0.2. If 20 people are in a class, find the probability of 3 A's, 5 B's, 10 C's, and 2 below a C. So as you can see right off the bat, I hope anyway, there are 20 total people in the class. Of those 20, we're going to break those into four categories: A's, B's, C's, and I'll label the last category as an F. So you can use your subscriptive variables to identify your categories and make things make a little bit more sense. But of our 20, we want to find 2 being an A. We want to find 5 of being a B. We want to find 10 that are a C. And we want to find, oops, let's backtrack. This was 3 that were A's, sorry, and 2 that are F's. So 3 A's, 5 B's, 10 C's, and 2 below a C. Noting that our X's, 3, 5, 10, and 2, add up to be our total number of students, or 20. So our X's should always add to be our N. And then we'll write our corresponding probabilities right next to each one. So the probability of an A is 0.1. The probability of B is 0.2. Of a C is 0.5. And the probability of below a C is 0.2. I like to put these side by side next to each other so that when I set up my formula, I know what exponent to set or raise each probability to. So that's why those are written in that format here. So plugging into our formula here, it is 20 factorial over 3 factorial, 5 factorial, 10 factorial, and 2 factorial. And then 0.1 raised to the third, 0.2 raised to the fifth, 0.5 raised to the 10th, and 0.2 raised to the second. So notice over here that 0.1 was raised to the third power, 0.1 to the third, 0.2 to the fifth, and so on. Okay, so that's why I like to write those side by side. From there, one other note I would make here, as you type this into the calculator, you need to put this denominator in parentheses. If you don't, and you just type it in as we have it written without parentheses, your calculator would do 20 factorial divided by 3 factorial, but then multiply that quotient by the rest of this, which would be the incorrect order of operations. So bottom line, put that in parentheses. If you put that in parentheses and type it out, you get 0.0058. You can always kind of check yourself to make sure that your answer makes sense. Is from our previous work, we've already established by definition probability falls between 0 and 1. And if you type this in incorrectly, you're going to get a large number, you know, in the tens or 20 or hundreds of thousands. So if you get a 17,580 as your probability, you know that's not possible. It's got to be a decimal value between 0 and 1. So you've typed something incorrectly or incorrectly, or you've set it up in not correctly. So make sure your probability falls between 0 and 1. Our second distribution is called a Poisson. A Poisson is used when a density of items is distributed over a given area or volume. What that means is you'll see a statement of we average an average number of items per something else. I'm going to refer to our example down here. We have an average number of 2 sales per day. So 2 sales per day would be our average per something else. And within our Poisson, we have a couple of new variables. E is a constant. If you did the second function on your calculator, second division sign, you get 2.71828, blah, blah, blah. Round to 2.78183, but you have this E function on your graphing calculator, so you might as well use it. Again, it's above the division sign, so use that as our constant, much like pi is with a circle. It's an irrational number, but it's using a lot of calculations here as we move forward in some of our math classes. Lambda is a new variable, so lambda, by a layman's term definition, is an average number we would expect to have for our sample size. So for example, let's say the city of Waukee averages 4, or a city of Waukee averages 4 robberies for every 1,000 people. Lambda would be how many robberies do we expect to have happen in a city of 20,000 people, so the average number for the 20,000 people. And then X is the number we're trying to find the probability of happening. Okay, so again, X is the number we're trying to find the probability of happening. Illustrated down here below, a door-to-door salesman averages 2 sales per day. Find the probability of getting 5 sales in a day if this approximates a Poisson. You can see from our formula up here, we simply need to identify 2 variables, lambda or X and lambda. X again is our number we're trying to find the probability of happening. We're trying to find the probability of 5 sales in a day, so X is 5. Lambda is the average we would expect to have happen, so we'd expect our salesman to get 2 per day if he averages 2 per day, so our lambda is 2. From there, we'll set up our formula. The probability of 5/2 is e to the negative second power times 2 to the 5th power over 5 factorial. And if we type that into our calculator, we should get 0.036. So there's our second distribution called a Poisson. Our third distribution is not going to be new, it's just going to put it in a formula form. A hypergeometric is used when trials are repeated but the outcomes are not independent. So this is very, very important here. This is what differentiates it from a binomial. A binomial, the outcomes are independent. The hypergeometric, they are not independent, so they're dependent. So our probability will change from one trial to the next. Essentially, if we select one item, like a defective part to test, we're not going to select the same item a second time. Now, it should look familiar because back in Chapter 4, we used our combinations. So notice that our categories here, our categories A and B, they add to be our total down here. And then we break our categories into the number we want out of each category, X and N minus X. They should total be this number here. Quick illustration here. Bag has 10 red and 20 blue marbles. If you pull 5 out without replacement, find the probability of getting 3 red and 2 blue. So we're pulling without replacement, which makes those dependent events, which makes it a hypergeometric. Okay? Because we have just red and blue, it could be binomial, but we'd have to replace the marbles, and we're not in this case, so it is a hypergeometric. So we start with our denominator, much like we did back in Chapter 4. We have 30 total marbles to choose from, and of those 30, we're going to select 5. Of our 30, 10 are red and 20 are blue. And then we want to find the probability of getting 3 red. So of the 10 red, we want 3. And of the 20 that are blue, we want to pull out 2. So 10C3, notice 10 plus 20 is a 30. The 3 plus 2 is the 5. That kind of our check to make sure we have our hypergeometric set up correctly. And if we plug that in, we get 0.15999, or about 16%, 0.16. So there's an example of each, a multinomial, a Poisson, and a hypergeometric. I have a few more to go through simply to decide which one we're going to use. In a large city, 50% of the people choose movie, 30% choose dinner and a play, and 20% choose shopping as a leisure activity. If a sample of 5 is selected, find the probability that 3 are going to a movie, 1 to a play, and 1 to a shopping mall. Okay, so this, because of the percentages, whether my first person or my last person is selected, there's still a 50% chance that they're going to choose the movie. So this is a multinomial, which will then tell me I wanted to identify my variables. So n is my total number of people. In this case, we have a sample of 5 people. We have people going to a movie, so x sub m, choosing dinner and a play, so I'll put a play, x sub p, and then shopping as our 3 subscripted variables. We want to find the probability that 3 are going to a movie, 1 to a play, and 1 shopping. And the probability of going to a movie is 0.5. Probability of going to a play is 0.3. And the probability of going shopping is 0.2. Multinomial formula then says 5 factorial. I'm going to go ahead and set up the parentheses just to hopefully remind us. And I have 3 factorial, 1 factorial, 1 factorial. Although I guess in this case I really didn't need the parentheses because 3 factorial is 3 times 2 times 1 or 6, and 1 factorial is just 1. But we'll continue on, and I have 0.5 raised to the 3rd power, 0.3 to the 1st, and 0.2 to the 1st. And if I plug that in, my probability is about 0.15. Okay, so moving on here. Checkout lane at a grocery store has an average of 5 people waiting. What is the probability of 7 people waiting if this approximates a Poisson? Tells us the Poisson, which means I just need these 2 variables, x and lambda. X is probably the easiest one to pick out because it's a number we're trying to find the probability of happening. So we're trying to find the probability of 7 people waiting in line. On an average day, we'd expect to see 5 people waiting in line. So lambda is our 5. So from here we have probability of 7, 5 is equal to e to the negative 5th power times 5 to the 7th power over 7 factorial, or we get 0.1044. Continuing, 10 people apply for a job as an assistant manager at a restaurant. 5 have completed college and 5 have not. The manager selects 3 applicants at random. Find the probability that all 3 are college graduates. I'll give you a little hint here. This is not a binomial because we're not going to select the same applicant 3 times, which means our probabilities are dependent, which makes it a hypergeometric. Our hypergeometric is our fraction bar. We have 10 people applying for the job, and we're going to interview 3. 5 have graduated from college, 5 have not. And we want to find the probability that all 3 are graduated from college, which means that we select 0 from the not college graduate column or category. 5 and 5 is 10, 3 and 0 is 3. Hypergeometric, we type this in, is 0.083. Let's get through a few more here. Our first one. Recent study found that 4 out of 9 houses were underinsured. If 5 houses are selected from 9, find the probability that 2 are underinsured. So to read through here, we're selecting 5 houses from 9. If I select the first house to check for proper insurance, I'm not going to select it a second time. So once again, it is a hypergeometric because the probabilities are dependent from one event to the next. Well, we have 9 total houses. We're selecting 5. Of those 9, 4 are underinsured, which means 5 are properly insured. So from our underinsured column of 2, we want to select 2. And from our properly insured, we also want to select, we want to select 3 because we'll select a total of 5. So we have 4C2 times 5C3 over 9C5, and that would get us a probability of about 0.476. 2 more to go here. There's a probability of 0.2% of a defective part in a shipment of computer components. Shipment of 500 components arrives. Find the probability of 0 defectives. This approximates a Poisson. So Poisson, x and lambda. X is the number we're trying to find the probability of happening, 0. Our lambda goes back to my definition. Definition is a number we would expect to have for our particular sample size. So in this case, 0.2% of our 500 is defective, so we'd expect to have, of those, we'd expect to have one that is defective, 0.002 or 0.2% times 500, or we'd expect to have one defective out of our shipment of 500. Okay, average number we'd expect to have defective for our sample size, in this case is 1. So we have e to the negative first times 1 to the 0 over 0 factorial, and we plug that in and get 0.3679. And one last time, it will look very similar to that problem. 1,000 cotton bolls were checked for boll weevils and 100 weevils were found. What is the probability of finding a boll with 2 weevils if this approximates a Poisson? Same thing yet again, x and lambda because of the Poisson. X is the number we're trying to find the probability of happening, which is 2. Now keep in mind that's 2 weevils in a cotton ball, so our lambda is our number of weevils per cotton ball, or 100 divided by 1,000, which gets us 0.1. Again, our average number, we expect to have 1/10 of one per cotton ball because they're spread over the 1,000 weevils, or 1,000 cotton balls, 100 weevils spread over that. Now our formula, e to the negative 0.1 times 0.1 to the first over 1 factorial, and that gets us 0.0045. And again, that covers our 3 distributions, a multinomial, a Poisson, and a hypergeometric.